Hello, hello. Welcome, everybody. We'll be starting this webinar shortly. I'll go ahead and give everybody some time to get into the room. Thank you, everybody, for joining us. Our webinar will be beginning shortly. In an effort to continuously improve course offerings, we've partnered with the education and research centers around the country to solicit feedback on educational needs. This survey is intended for employers, HR personnel, and anyone responsible for determining what continuing education and trainings are offered to employees. I'm going to put the link in the chat and welcome participants to complete the survey following the webinar today. I'll also send it out a little bit later towards the end to make sure that anybody who didn't see it earlier will have the opportunity to do so. Thank you in advance for supporting us. Michael, if you can go to the next slide, please. This is information on our upcoming health-centered agriculture education program. We will also be taking some survey information on this. You can follow the site on here at the bottom of that photo if you'd like to learn a little bit more about that. So first, our upcoming courses. Wednesday, November 17th, Effects in Chronic Heat Stress and Shift Work on Postural Stability in Firefighters, a pilot study in partnership with Rachel Zeiler, PhD candidate for the University of Cincinnati Education and Research Center. Due to high demand, we've added 3 new course dates for assessing ventilation for COVID-19 mitigation, a hybrid online and in-person hands-on course where learners will get hands-on experience using bolometers and collect and analyze ventilation data with David Moore, CIH. The next offering will be December 13th through the 14th, 2001. You can find more information about this on our website, coeh.berkeley.edu/about-CE. We'll also be offering an OSHA 10 construction course December 7th through the 10th, 2021. This hybrid online and in-person training will instill safety awareness with an emphasis on hazard identification, avoidance, control, and prevention. I'll go ahead and put links to both of those in the chat shortly. On behalf of the Education and Research Centers throughout the country, we are pleased to present the Industrial Hygiene Webinar Series. This collaborative effort on behalf of each of the ERC's continuing education programs aspires to provide access to current research supported through NIOSH ERC programs. Thank you all for joining us. Today's webinar, Elevator Ventilation and SARS-CoV-2 Particulate Matter Removal, is brought to you by the Northern California NIOSH ERC, Michael Kado, MPH, and Dr. Kathy Hammond, PhD, CIH at the University of California, Berkeley. A few housekeeping items first. You will all be muted during this presentation. If you would like to ask a question, please enter it into the online Q&A box, not the chat. We will save time at the end of the presentation to address as many questions as possible. This presentation is being recorded and will be made available on the Center for Occupational Environmental Health YouTube page. All participants who have logged in today with their registration email will receive an email tomorrow with a link to the evaluation form that will qualify participants for a certificate of completion worth 1 continuing education contact hour. Once the evaluation is complete, you'll be able to access and print your certificate. Along with that email, you'll also get a recording, a link to the recording and any resources that come from this presentation. At this time, I'm pleased to welcome our presenter, Michael Kado, MPH. Michael is a doctoral student in industrial hygiene at UC Berkeley School of Public Health and Environmental Health Sciences. He earned his MPH in industrial hygiene from UC Berkeley, as well as a BS, Bachelor of Science in Human Physiology from the University of Oregon. His research interests focus on understanding the implications of ventilation on exposure to particulate matter in crowded occupational settings during a pandemic, assessing the implementation and mitigation effectiveness of plexiglass barriers against SARS-CoV-2 transmission for frontline workers, and assessing occupational exposures within emerging recycling industries. Thank you so much for joining us, Michael. I'll go ahead and let you take over.
Thanks, Jessica. All right. So that was a great, excuse me, that was a great introduction. Again, I'm a doctoral student here at the Berkeley School of Public Health. And thanks for joining me today for this talk on elevator ventilation and SARS-CoV-2 particulate matter removal. So first off, I'd like to acknowledge my collaborators on this work that I will be presenting today. First, I'd like to thank my advisor, Dr. Catherine Hammond, and other Berkeley Exposure Assessment Research Lab, or colloquially we're known as the Bear Lab, Dr. Snoth, Dr. Pertula, Charles Perino, David Moore, Pat Nguyen, and George Shun, and all the other members of the group. I'd also like to thank the support from the Center for Disease, the CDC NIOSH Targeted Research Training Program, and the Northern California Center for Occupational Environmental Health. And finally, to all the building managers and elevator consultants for their expertise on this project. So first, I'm going to give an interview of what I'll be talking about today and with regards to elevator ventilation and particulate matter, or PM removal. I'll be using those terms interchangeably. PM is particulate matter, short for that. So the table of contents, first I'll talk about the learning objectives of today, some background, including ventilation overview, the project overview, what did we examine, and then more in depth for our experiments that we performed, such as the normal use experiments of an elevator, intervention experiments, summary of the findings, and discussion and future directions of this work, and then finally questions at the end. So the learning objectives for today's talk are to review the basics of ventilation assessment within elevators, describe the effect affordable and easy to implement interventions have on ventilation and particulate matter removal within elevators. And finally, discuss the implications for elevator use during a pandemic. So getting into the background behind this and motivations behind this research. COVID has wreaked havoc and created a new normal for everyone in the world and has killed over 5 million people and infected 249 million people worldwide as of November 2021. It's well established that the SARS-CoV-2 virus is transmitted through the aerosol route in shared spaces. And this figure is from Wang et al., published earlier this year. And it's a great diagram that shows an infected person on the left here, emitting smaller particles from the lower respiratory tract, as you can see at the bottom here, and denoted by these smaller circles, and larger particles from the upper respiratory tract. And these are, this is showing coughing or sneezing to a potential host here on the right. From that cough or sneeze, we see the larger or heavier particles are droplets, as shown in the red box. And they drop out of the air rapidly within 1 to 2 meters due to gravity. And this is mainly due to gravitational settling. Again, a droplet is a larger particle that drops out and it doesn't travel very far. And usually it falls to the ground within 5 seconds. Of course, this depends on the size of the droplet. This is just very generally. In contrast, an aerosol, typically smaller than a droplet, is a suspension of particles in a gas. The particles can be a solid, liquid, or a combination, and they can travel much further, as seen in the red box, originating first from the infected person, again here on the left, to the potential host on the right. And they can move beyond a meter, which is important for SARS-CoV-2 transmission. Suspended particles have a residence time in air for more than a few seconds and can be carried along with air currents. Knowing that these aerosols or particles can stay suspended for longer amounts of time is important because we also know the virus is viable for minutes to hours in aerosols and other surfaces as well. Many aerosols, however, are typically smaller than 5 micrometers in aerodynamic diameter, but it's not a hard and fast rule. Typically in the literature, it has showed that though. The size of the particle or the aerodynamic diameter is important to understand how the particle behaves in the air. On the right, you can see an emitted aerosol with the virus encapsulated in the respiratory fluid, as shown here. When the virus-filled respiratory fluid is expelled from an infected person's lungs, the movements are determined by the particle size. And over time, as you see here on the right, this respiratory fluid evaporates, creating smaller sized particles that can stay suspended in the air longer. And the SARS-CoV-2 virus itself is 0.1 to 0.2 micrometers in aerodynamic diameter, but is often larger because it is contained within these respiratory aerosols or droplets, which are emitted from people, which typically are larger. And it varies based on the source of these, the source of the aerosol or droplet production, i.e. like a cough versus a sneeze versus just breathing. And we care about the size, as previously mentioned, because it affects how long it stays in the air, how far that aerosol can travel, how quickly it falls out of the air, how it interacts with the airflow, where in the lung the PM deposits, so the health effects, and then it relates to the health effects, and then how it's removed from a given space. This last point, how it's removed from a given space, is what I'll be focusing on in today's talk. Removal of PM from a space is one method to reduce transmission of SARS-CoV-2, as previously mentioned. And also during the pandemic, there's been a layered approach towards mitigating transmission of the virus. Here we have the Swiss cheese model. Each slice of cheese represents some sort of control to reduce the transmission of SARS-CoV-2. And each slice, like a piece of Swiss cheese is imperfect. It has holes in it. But however, when combined with other pieces of cheese or controls, these holes can be covered by another one. So together they form a stronger response or a stronger control response. For today's talk, I'll just be focusing on one slice of cheese or one control, ventilation and outdoor air and air filtration. Excuse me. So air changes per hour are the standard metric for ventilation rates. And the air changes per hour are the ventilation airflow rate measured in cubic feet per minute times time, which is 60 minutes an hour, over the volume of the space. And each air change per hour reflects air flowing into and out of the room corresponding to the volume of the room. So for example, here on the bottom, consider a room that's 10 by 8 by 5 feet or 400 cubic feet. To achieve 2 air changes here on the left, one would have to supply 800 cubic feet an hour or 13.3 cubic feet a minute. So for our study, the air change rate or air changes per hour is the decay rate of aerosols or tracer gases as their proxies for ventilation inside of an elevator. By understanding decay rates of particulate matter and tracer gases inside an elevator, we can calculate the air change rate. This is a very important concept for today's talk. By measuring the rate of decay of these aerosols or particulate matter or tracer gases inside the elevator, it gives us an idea of the ventilation. So visualizing air changes per hour using particulate matter removal mechanisms. Let's just say this is a box or an enclosed box with some outlets for air. And you have a particle generation source in the middle, as shown with the black box. And for these particles to be removed from in space, there are four first order PM removal mechanisms that we'll be focusing on today. The natural ventilation, which is the method of supplying outside air or outdoor air into a space using non-mechanical forces. Escape through cracks. Think of like an open window or grates. And this is relevant for smaller particles and larger particles. Next, we have gravitational settling of particles. And this is relevant for larger particles that fall out due to gravitational forces. Next, we have impaction of high inertia particles impacting onto the surface of elevator walls. And then finally, we have diffusion, which is the random motion of gases and very small particles in air, and then they deposit on the wall. So since this applies mostly to really small particles, it's perhaps less important in today's talk, but it is overall an important mechanism for virus removal. And together, these three, impaction, diffusion, and settling, today are called deposition. However, it's also important to acknowledge there are other methods of PM removal, such as interception and electrostatic effects. But these three have been found to be most relevant for this type of study. So again, an important concept from that previous section is by measuring the rate of decay of particulate matter and tracer gas inside an elevator, we can calculate the air change rate. So now that we've talked through a bit through the background information for today's talk, let's talk about the project overview. We're amidst workplace reopenings, and crowded, close contact, and poorly ventilated indoor spaces are of greater concern due to well-documented airborne transmission of SARS-CoV-2. But ventilation and understanding of infectious particle removal within crowded elevators are not well understood. Potential exposure within these elevators is a concern for the virus. With the development and wide distribution of vaccines, people are returning to the workplace. However, with the emergence of highly infectious variants of the virus, potentially lower concentrations of aerosol might pose higher risks than previous variants, and combined future research should be done to determine ventilation rates and PM removal from elevators. So the research project goal is to assess elevator ventilation and determine removal rates of PM by measuring natural ventilation and deposition of particles in elevators during normal use in 3 intervention scenarios in 3 elevators. So here's some elevator use statistics. Well, first of all, elevators are ubiquitous. In the US, there's an estimated 900,000 elevators, serving an average of 20,000 people per year. Collectively, the US elevators make 18 billion passenger trips per year. And the majority of these elevators are within commercial, retail, or residential properties, averaging 4 to 5 floors, or an equivalent of 40 feet. Each elevator averages about 5 people per trip. So why do we care about ventilation and PM removal in elevators? So as outlined before, elevators are potentially crowded spaces that have complex and variable ventilation scenarios. Riders are potentially vulnerable to exposure. Some evidence of indirect elevator transmission early on in the pandemic was found in China, which found indirect transmission in a shopping mall among symptomatic and asymptomatic cases. Concerns from the public about safety of riding in an elevator amidst a pandemic. And we're addressing some of the gaps in this knowledge, such as what are the baseline ventilation rates of elevators? How long do potentially infectious particles remain suspended in an elevator space? And what interventions increase ventilation rates and by how much? And our hypothesis is that easy to implement interventions will increase the ventilation rates inside an elevator compared to baseline ventilation. So what do we examine? Here's the experimental campaigns. 3 elevators were investigated in the San Francisco Bay Area from August of 2020 to January of 2021. And these 3 elevators were chosen based on the year of construction. And after talking to a few elevator consultants and elevator technicians, when an elevator is installed, most of the time the cabin or ventilation isn't really altered unless it's required. So most of the time once it's installed, it's usually not adjusted. And usually control safety panels are the things that are updated and changed in elevators. So this was part of the motivation behind choosing 3 different elevators. Sodium chloride was used as a surrogate for SARS-CoV-2 and CO2 to calculate ventilation rates. And 6 different experiments were done in triplicate. On the right here is our experimental setup in one of our elevators. And let's start at the top left. Here's the instrument inlets, and these were placed in breathing zone, which was about 5 feet is what we represented it as. Next, we have the nebulizer in the bottom left, and this is what created our aerosol inside the elevator. And finally, the release point of this aerosol to increase the concentration inside the elevator. So next, I'll outline some of the normal use experiment approaches that were used to capture the elevator phases. So an elevator, you can think of it as either stationary, as just sitting, waiting for a passenger with doors closed. And this represents the time in between riders. And the purpose of measuring the stationary phase is to see what the baseline ventilation is without riders, without any movement, just the elevator sitting there. Next was we looked at a moving elevator, and what we did for these experiments were moving the elevator from the bottom floor to the top floor and back for at least a few trips. I believe we did it for a few minutes. And the purpose of measuring the moving phase was to see what the baseline ventilation during a moving scenario was, or a moving phase. So the two things we can take away from having both these phases, we can get two things from this, is that we can see what the difference in ventilation between a stationary elevator and a moving elevator, but also we can use these as a piece towards recreating an elevator scenario at a later time in terms of PM removal. So our first experiment was using CO2 inside a stationary elevator to determine the natural ventilation. And here's a general overview. Again, let's say this box is an elevator. Natural ventilation is moving both in and air out due to non-mechanical forces. And the CO2 was used to estimate natural ventilation because it's an inert gas. It's not chemically reactive. It doesn't deposit onto walls. And it can only really be removed through natural ventilation or through grates or cracks in the elevator. So by measuring the rate of the decay of the CO2, we can get natural ventilation of this elevator. Our second experiment calculated the ventilation rate by measuring the decay of aerosol inside the stationary elevator. The particles are removed primarily through deposition. So by measuring the rate of decay, we get the ventilation rate. And the third normal use experiment is have that same scenario I just talked about in terms of having an aerosol particle inside the elevator and then observing the decay. But instead of just having the elevator sit there, we move the elevator. So I'm going to go in a bit more detail for experiment 1, and all the following slides will go into more detail of the experiments. So again, as previously mentioned, natural ventilation is moving air in and out of a space using non-mechanical forces. And to measure the natural ventilation in a space, a tracer gas, CO2, again, can be used. Then what we did is we mixed the cabin of the elevator while the CO2 was generating to get an even concentration throughout. And it was measured using a TSI Q-track, which measures in ppm, or parts per million. So again, this picture on the left should look familiar. This is inside the elevator. This is our experimental setup. And on the right, you have, there's a graph of the Q-track output. So here's how we measure the natural ventilation. On the y-axis of this graph is the natural log concentration, and the x-axis is in time. So I'll talk through all the points of how we went from this graph and this data to getting a ventilation rate. So the first point labeled here as 1, this is when we put inside the elevator a CO2 source. And the goal of this was to increase the concentration inside the elevator. And we mixed it with a fan. Then point 2 on this graph shows that we reached a sufficient concentration of CO2 after 5 minutes of generation. And the source of CO2 was taken out of the elevator. And we determined that 5 minutes of CO2 generation was sufficient by doing some preliminary experiments on this, testing different time periods. And then the third point, right before this, you let the air stabilize inside the elevator, and then a decay slope was measured using a linear regression. And here's the output of that regression. And the important piece that we're trying to get from this regression is the slope, which is the K value up here. And what that represents is it's the natural log concentration of the CO2 over the time period that we're looking at, as denoted by this blue line. So this is the rate of decay of the CO2 inside the elevator. So that's really important. This rate is in ppm per second, and we convert that to air changes an hour given here. And here's what we found across all three elevators. The 1940s elevator, the gray one on the left, had an average air change rate of 1.85. Our 1960s elevator was 1.82, and our 1980s elevator was 3.36. And together, the average air change rate was 2.3. And notice there are some differences between elevators. This wasn't quite expected, but it's interesting to see. And we see between elevators, there's even a potential fold change, or almost a fold change, excuse me. So next, I'll talk about our second experiment, which was during normal use of an elevator in a stationary elevator and looking at the particle deposition. So our goal for this experiment was to use a PM2 aerosol to spike the elevator and observe the decay rates. So on the left, you see the nebulizer that we used, and it was used to generate the aerosol or increase the concentration inside the elevator. The graph on the right shows the sizes that are generated from this nebulizer, which are PM2. And the size fraction is relevant for non-coughing and non-sneezing scenarios and would best translate to breathing scenarios. Just breathing produces smaller size fractions of aerosol. To measure the particle deposition in a stationary elevator, again, a PM2 aerosol was generated inside the elevator. And again, there's this black box that creates our particle generator or nebulizer that generates this PM. And the decay is observed using a real-time instrument, a TSI side pack, which measures in milligrams per cubic meter. Again, this is going to look familiar, but I believe it's important to walk through each experiment because there are differences between them. Again, on the left is the experimental setup inside the elevator, and then on the right is the graph. So the first point is to increase the concentration inside the elevator so that we can observe a decay of the aerosol. Next, after 5 minutes of generation, a sufficient concentration was reached and the generator was stopped. Then the decay of the aerosol was measured using a regression, and the output of the regression was in concentration, or milligrams per cubic meter per second. And again, this rate of decay is our ventilation rate. And we changed that to air changes an hour. And what we can see is in our 1940s elevator, we got about 3.51 air changes an hour, and our 1960s 1.8, and our 1980s 1.57. And on average, we had 2.4 air changes an hour between all three elevators. So next, taking that air change rate value from our first two experiments, again, this 2.4 and previously the 2.3, we can visualize this decay. So that air change rate gives us the ventilation rate, but you can take that ventilation rate and put it into an exponential decay equation as shown here. And the input would be each ventilation rate from each experiment. So remember, we did 6 experiments today, or we did 6 experiments for this project. And for baseline stationary, what we're going to look at, what we looked at was the first 2 experiments. So you put them into this equation, and it'll give you a visual over time of the decay of this theoretical concentration of PM. So here's what we have. So on the y-axis, it's the percent of particulate matter remaining inside an elevator at breathing zone. And this is just a theoretical, well, this is just a percentage. We're not going into actual concentrations, but just a percentage of a concentration. And then time is on the x-axis. And what this shows is with the natural ventilation, which is our first experiment, and particle deposition, which is our second experiment, this is our baseline removal. And the red line denotes the 50% removal of this PM. And what we see, it takes about 9 minutes to reach 50%. And it's important to interpret this very specifically. So this scenario doesn't represent all scenarios. What this represents is if an individual emitted, like say coughed or sneezed into an elevator, and then they left, and the elevator just stayed there stationary with doors closed. It would take about 9 minutes on average between all three elevators for the concentration of the particles in the elevator to get to 50%. So half the particles are removed by that time. So I'll be repeating this with our other experiments too, but I think it's an important tool to visualize what does that actually mean for PM removal. And this part of our air change rates and then visualizing this way, they're all small parts of a larger puzzle that I'll talk about a bit later for future direction research. So next, the third experiment, which is normal use. And we're looking at when the elevator moves. Again, the elevator was spiked with a concentration of an aerosol, and then the elevator was moved and measured using a side pack in milligrams per cubic meter. So again, this is going to look familiar, but the elevator concentration was increased for 5 minutes. It was removed. The source of aerosol was removed or turned off. The elevator was then put into a continuous moving cycle. And meanwhile, while it was moving, the decay of the aerosol was measured. And then you get an output. Again, the slope from this equation is the important piece, and that's our ventilation rate. And notice when it's moving, compared to stationary phases, which we see on the left, once you start moving, the average is 18 air changes an hour, which is on average almost 6 to 9-fold increase, which is pretty big. And in our 1940s elevator, we have 24 air changes an hour. Our 1960s, about 11 or 12, and then 1980s was about 17 to 18. So again, taking these ventilation rates, and let's visualize this in an elevator, let's visualize this in terms of particulate matter. So again, taking this equation, but notice how this term right here changed. Instead, it's just the ventilation rate from the third experiment or the moving experiment. You input it here, and the output is the percent particle concentration at time t, again with this graph. So what you're looking at here is the blue one, again, is the baseline stationary of natural ventilation and particle deposition. And remember, that took about 9 minutes to reach 50% concentration of PM. Now for a moving scenario, just the elevator moving up and down with the doors opening at each stop, it takes about 3 minutes to reach 50%. So again, to put this into context, this represents if this scenario represents if someone were to cough into an elevator, get off at the bottom floor, and someone were to recall it at the top. This is the rate that you would observe. Again, future research, I will talk about how to reconstruct that into multiple different scenarios at once. So now let's go into the intervention experiments. And again, they're aimed at enhancing particle removal. So the first intervention was propping the door open of the elevator, and we propped the door open for 5 minutes after spiking the elevator with aerosol and observing the decay. The second was adding an air purifier during a stationary phase, and this air purifier was a HEPA filter. And then finally, that same air purifier was added in during a moving scenario, a moving phase of the elevator. And all three of these interventions were chosen based on feasibility and cost to implement in multiple types of elevators. And here's the fourth experiment more in detail. Again, here's the elevator with a particle generator in the middle and an open door, and that would remove our hypothesis. It would increase the ventilation inside the elevator. And then the side pack to measure the concentration over time. And again, we spiked the elevator with the aerosol, and then for 5 minutes, once the concentration was sufficient, we opened the door for 5 minutes. Meanwhile, while the door was open, we took the decay of the aerosol from the elevator. And the output again is the slope. And here's our results. Notice the change in the y-axis. The average is about, well, the range is 33 to 180 air changes an hour between all three. Notice there's quite a big difference between three elevators. And the reason for that, we're still investigating, but it's interesting to note that an open door does increase ventilation compared to normal scenarios. And again, taking that ventilation rate and putting it into this equation so that we can visualize it. And again, notice that this is the fourth experiment. And remember the baseline, the blue line of natural ventilation particle deposition took about 9 minutes to reach 50%. However, with open door, it takes less than 1 minute to reach 50%, which is quite quick. And I'll talk more about that more in depth a bit later. But again, this scenario would be if someone were in the elevator, were to eject or emit into the elevator and then prop the door open. This is what we would observe. So the fifth experiment is another intervention. It's looking at the stationary elevator plus an air purifier. Again, here's the elevator with a particle generation source, and we add in an air purifier, portable air purifier into it. And we measured this again using a side pack. And to calculate the settling and deposition of the particles within the elevator, an aerosol was generated for 5 minutes. Once a sufficient concentration was reached to observe a decay, the source was turned off. Then we turned on the air filter inside the elevator and observed the decay. And again, the slope of this decay is our air change rate in concentration, or milligrams per cubic meter per second. And as you can see, the range was 20 to 34 air changes an hour between elevators. And something interesting to point out here too is in our 1940s elevator, there virtually wasn't any difference between the open door scenario, which had 33, and adding a air purifier, which is quite interesting. And I think, again, like I mentioned before, we're still looking into the data and seeing what is the reason behind this difference between the three for the open door scenario, and why the air purifier scenario or intervention is similar. So again, we take that air change rate, the average of the ones previously shown, and put it into this exponential decay equation so we can visualize the PM decay. And blue's baseline, this should actually say 9 minutes, but what we see is about 2 minutes to reach 50% concentration, which is still an improvement. All right, and now on to the last experiment, which was using the air purifier plus moving the elevator. Again, here's the elevator. We'll increase the concentration inside of it, add an air purifier, and then also, while the air purifier is running, to have the elevator move, and it will be measured using a set pack. So the concentration inside the elevator will increase for 5 minutes to get us to a sufficient concentration. The air purifier was turned on, and the elevator was moved. And the decay of this of the concentration of particles was observed, and this decay is our ventilation rate. And as you can see, these look a little bit more consistent between elevators, and the average is around 44 to 45 air changes an hour, and the range is 43 to 48 air changes. And again, if you're to compare this to our other interventions, it's to our baseline or our normal use scenarios, it's still an increase. And between interventions, I will talk about shortly. So again, taking that average ventilation rate, putting it into this exponential decay equation to visualize it. And what we see is about a minute to reach 50% concentration. And like previously, this represents if someone were in an elevator with an air purifier, they were to emit into the elevator, get off the elevator at the bottom floor, and someone at the top floor recalled this elevator. This is what this represents. And again, I really want to emphasize, these are all pieces of the puzzle. And the purpose of these experiments were to isolate specific aspects of an elevator so that we could recreate different scenarios. So let me talk about the summary and discussion of the findings. As you can see, the elevator exhibited a wide range of ventilation rates. The range of the average air changes per hour was 2 to 116. And generally, as you can see, moving and interventions increase ventilation rates. So everything from here on compared to these two increase the ventilation rates. And there's also, we observe differences between elevators, between different eras when they're built. And the removal of PM through air changes shows that interventions are improvements upon a stationary elevator, as shown here on the left, the interventions and the normal moving scenario versus the baseline concentration, baseline experiment. So now to compare the interventions of the open door versus the air purifier, as shown here. Again, the average ventilation rate of the open door experiment was 116 air changes an hour, and the average ventilation rate of the air purifier while it was stationary was 27. And I think the takeaway from this, it's really interesting to see that the air purifier during a stationary elevator seems much smaller than an open door scenario. But let's observe that. What does that actually mean? And what we see is when during the open door scenario, it translates to less than 1 minute to reach 50%. Whereas if you have an air purifier in there, it's about 2 minutes to reach 50%. And again, these are both during stationary phases. So it's important to consider these for recommendations for elevator use, that both of them seem to be useful in removing PM inside an elevator. And then comparing the normal use moving scenario versus the intervention of moving scenario. The ventilation rate during the normal moving experiment is less than half than the intervention scenario of adding the air purifier while the elevator is moving. And basically the take home from this is that the air purifier improves ventilation compared to normal use. And this visually represents it as well. So to summarize everything, simply moving the elevator compared to having it just stay there increases the ventilation rate and removal of PM, which makes sense. Adding in an open door intervention increases the ventilation rate and removal of PM. And adding in an air purifier intervention increases the ventilation as well. So in terms of general discussion, some research gaps that were addressed in the study were, what are the baseline ventilation rates of elevators? How long do potentially infectious PM remain suspended? in an elevator space, and what interventions increase ventilation rates, and by how much. And in further discussion of one of the interventions, the open door and air purifier interventions improve ventilation rates and PM removal. But in talking with some building managers, elevator technicians, and an elevator engineer, having an open door intervention might not be as feasible as we originally thought when we planned these experiments over a year ago. And the reason behind that is for safety reasons, ultimately. You can't prop a door open. It might change the recall. Someone might trip over what you're propping it open with. It wasn't really generally recommended. It might not be as feasible to use that intervention. And then the air purifier intervention is our recommendation. So how about riding an elevator as we all do, as we return to work or go into public spaces? I think it's important as a rider, and then also for building managers, to keep having this layered approach. So this is the Swiss cheese model again. So the riders can take a personal responsibility approach, as shown here on the left side. So like social distancing, hand hygiene, masking, maybe avoiding crowded situations. For example, if there's an elevator with multiple people in it, perhaps you might want to use an alternative route to get to the floor you want, or maybe just not ride directly with those people. And then shared responsibilities as for all of us, for example, testing, ventilation, quarantine and isolation, and of course, vaccines. So again, continuing to use this layered approach is important. So for next steps, as I was alluding to earlier in the talk, this project isn't quite finished. This is still a work in progress. All those experiments that I went over in detail today, those are just smaller pieces to the puzzle. Our larger goal of this is to create a consecutive elevator ride recreation. And my hypothesis is that consecutive rides would create some kind of cumulative concentration effect. So after one rider, let's say an additional rider would get on, and that would increase the concentration of the elevator. It's a very dynamic process, and it might take longer to get down to baseline if it's a busy time with more people. So that's something that as a research group we're looking into. And the benefit of this is we have empirical data to help support this recreation of those rides, which I think is a strength. And you can recreate all sorts of different scenarios with that. So for some closing statements, again, the learning objectives for today's talk were to review the basics of ventilation assessment within elevators, describe the effect affordable and easy to implement interventions have on ventilation and particulate matter removal, and discuss the implications for elevator use during a pandemic. And a summary, again, is simply moving the elevator and intervening with the elevator increase the ventilation compared to an elevator just sitting there. And some strengths of this study are primary data collection or empirical data during realistic scenarios, an industrial hygiene perspective towards this, which is how can we actually apply this in a real setting, and how can we work with stakeholders that are involved with elevators and ventilation in buildings, so that not only can we do thorough science, but how can we actually implement it so it's actually used? And then focusing on representing PM from a breathing emission and not on cough simulations. And then testing easily implemented and cheap interventions for elevators. And the public health significance of this is we showed that interventions increase the air change rate by at least an order of magnitude to be conservative. And in case of the open door intervention, on average, we saw 2 orders of magnitude increase compared to a stationary elevator. And this research provides more evidence for understanding the PM removal in elevators. And this can help building, hopefully this can go towards future literature and building managers who are using different elevator protocols. and potentially could be used in other scenarios, say if there's a future pandemic or flu season. I think we'll be more informed for elevator use at a later time. And again, none of this is possible with all these wonderful scientists and elevator experts. And are there any questions?
Thank you, thank you. And if everybody can please add your questions to the Q&A box versus the chat, I will be answering, or I'll be asking them from the Q&A box, not from the chat, which is at the bottom normally of your screen. Okay, so the first question, and also thank you so much for that presentation. It seems like we have a few questions over here and maybe some more to come. So the first question is, did you measure FPM, CFM, et cetera, as a control for your estimation method of ACPH?
So we didn't. The approach that we took, we used the decay method. I think, you know, if we could take that approach, we could take the elevator and try to estimate and identify all the different ports and measuring that. But at the time, this was the approach that we chose to undertake.
I actually see here that there's a secondary part of that question. They wanted to know what, if any, traditional ventilation measurements were taken for control and comparison, any smoke visualization, tape lift, or wipes for particle deposition. How do you back up, double check, control for your estimate methods?
Yes, so during the open door scenario, I believe what we did use a tracer smoke that the air was going out. And another part of this project, we wanted to originally use a metric like face velocity measurements or open door velocity measurements and seeing which way the air goes. And we used a qualitative tracer smoke for that. But other than that, this is the approach that we took.
Thank you. And with regard to the particle deposition, when you showed the value for ACH for particle deposition, did you remove the effect of natural ventilation?
Yes, that's a great question. We did, because the values for particle deposition would include natural ventilation. The values that you saw today include the natural ventilation subtracted out of it.
Thank you. Let's see, next question. Did you measure background particulate in the shaft of the elevator?
Oh, that's a great question. We did not measure the background particulate in the elevator shaft. We did take background measurements inside the elevator. But the main point of this experiment, we weren't really looking at absolute concentrations. We were looking at the rate of change of concentrations. But I think that would have been a good step to take for further QA/QC steps.
Okay, great answer. Let's see, next question. What were the physical differences between the elevators other than date of construction, size, general HVAC or lack thereof, length of time that the door stays open between button pushes, et cetera?
Yeah, oh, that's a really great question. So there's differences in volume, of course. The walls as well were different materials. For example, in our first elevator, the walls were steel versus the second elevator is carpeted. So that would make some differences in terms of deposition. But that's something we're still looking a little more into. These results are still a work in progress. And in terms of mechanical ventilation or HVAC inside an elevator, the people I talked with that were in charge of these, it normally doesn't have any mechanical ventilation running, which is something that we would like, that we would look into in the near future to include an elevator that does have mechanical ventilation that is constantly running.
Thank you. Okay, next question. Was your choice of particulate size cut point of 0.3 based on the limits of the TSI particle counter? Model 9110 goes down to 0.10 UM.
So the cutoff for that, I believe, was based on instrumentation, and then also, I believe it was based on instrumentation, but also, I think the limitations were based on the aerosol that we were able to produce. So it was based on the nebulizer that we had.
No, Michael, you're right. In the first case, it was the limitation of the instrumentation.
Mm.
And the side pack only can detect at 0.3. So it's a good point, because the particles could evaporate to smaller than 0.3, but still greater than 0.1. So that is a little gap that is missing.
Thanks, Dr. Hammond.
Thanks for answering that, Kathy.
All right, let's move on to the next question. There's a natural thermal rise in elevator shafts. Did you consider whether or not that had any effect in the particulate removal in the car?
Yeah, that is something that we, in discussions within the group that we had, is that I think that's something that we would have to look into further, because thermal rise and number of floors would potentially play a role in that. But I think that's a great question. And I think I don't have a great answer for that right now, other than I do acknowledge it. Yeah.
Thank you. Let's see. So how do the variables such as air dispersion, ventilation, and the number of passengers in the elevator affect the contamination rate or contamination on a person in the elevator, given its limited occupying space? And a secondary question similar to that, somebody else asked also how much time on average did the passengers ride the elevators, if that had anything to do with variables.
Okay, so the purpose, I think, let me answer the first question first. So the number of people in the elevator would alter the concentration inside the elevator, but what we were looking at was purely ventilation rates and not a continuous emission. So our experiments represented just a single concentration, so like a single bolus into the elevator to estimate the ventilation, to calculate that ventilation. Whereas if you had more people in it and people going in and out of it and variable different scenarios of that, it would change the concentration through time. And that's the next step of this study, is that we're going to try to look at that. I do also want to point out that this study does not get into infection or risk of infection or dose of SARS-CoV-2 or any of that. This is purely just the PM in an elevator, and that is sort of outside my expertise at this point, and it focused just on the PM removal. And I'm sorry, Jessica, what was the last question?
Oh, and the second question to that was also as a variable, how much time on average passengers ride the elevators?
So I don't know on average, but I guess it depends on the building. For our elevators, going from the bottom to top floor was, I think on average, 30 seconds to close to a minute. And it also depends on how many floors and how many stops there are. So I don't have like a perfect average number for that, but that's a good question. And I think that's important to understand, especially for the 15-minute exposure for 24-hour rule, which again, this study doesn't specifically go into that, but I think it's an important piece.
Yes, absolutely. Let's say we have two more questions. If anybody else does have any questions, please let me know in the Q&A box, because we're going to wrap up soon. Following up on background measurement, were the elevators cleaned before the experiment? It would be another variable if one was dusty and the other had just been cleaned.
No, that's a great question. I think what this question gets to is the concern of resuspension. And I think that's a really good question. In terms of cleaning the elevator, we use a standard practice of trying to air the elevator out before, but in terms of wiping down every surface, that was not quite the goal of this. I think that's a really great point, though.
We're about to have to wrap up soon, so we'll answer. bunch of questions just came in at once. I don't know if you have time to answer a couple more, but I think 3 people just put them through at the same time. Let's see. Also, were the depths of elevators from the door to the back wall where you monitored particles different? And would this account for any differences in the doors open measurement?
That's a good question. So the distance from there did vary a little bit. And I assume it might make some difference, but what we did is we did ensure that the placement of the monitors we placed in an area where we thought someone would stand, which is furthest from the door in the furthest corner, opposite of the controls, and that's where we placed it. Distance from there would make a difference, so that's an important point. Yeah.
And let's see, when you were looking at moving elevator, did you look at the rate of the speed of the elevator and the effect on ventilation rates? Would the taller buildings have greater speed than, say, a 4-story building, which maximizes the time in the elevator and possibly a greater ACH?
So we do have the times of the excursion times, like going from the bottom floor to the top floor for the different buildings and elevators. I don't know them off the top of my head, but it would affect time in the elevator.
Let's see, okay, 2 more real quick if you have time. Did you measure potential pressure differential between shaft and car?
That's a great question. That would definitely affect it. We did not measure that. Especially during moving scenarios, that would be more relevant. And by doing the moving scenario, we're assuming that we're accounting for those pressure differences between the shaft and the elevator, and that will play a role. So a lot of these experiments, they take into account some of these variables that are mentioned, and they're kind of assumed to be in there. In terms of teasing out how much of an effect that is, that wasn't really our outset goal, but it would play a role.
Thank you. And the very last question, your particle deposition rate corresponded to about 2 ACH. Do you find that surprisingly high value for small particles, at least in the context of gravitational settling?
Yeah, so that's a good question. So for aerosols at 2 air changes, so for smaller, that's a good question. So I think, again, for the particle deposition experiment, we did take out natural ventilation. Perhaps, I think that would be a little bit on the higher end for such small particles. And I think that's a very thought-provoking question that perhaps we should look into a little more.
Thank you so much. And again, thanks for being here. Thank you for presenting on all this valuable information. We will be sending out a copy of the webinar recording tomorrow with the link for the evaluation for the continuing education credits for all of those who are here today. Anybody who wasn't able to make it, if you have any peers, if they registered, they will be able to get a copy of that as well tomorrow. Yeah, thank you, Dr. Hammond, for being here today and for all of the audience presentation. It's been pretty amazing. And again, if anybody needs to reach out for any reason, you can contact us at coeh.berkeley.edu/about-CE. And again, we just want to make sure that we can, if anybody would like to fill out the survey for the CE needs survey, I'll put the link one more time in the chat before I close it out. So everybody have a great rest of your day and enjoy all this information. Take care.
Thank you.